Oh my God, I can't believe it. Like the moment has arrived. We're about to learn conservation of energy. Here we go. Okay, so we've phrased it several ways so far, but I'm going to phrase it one more way. It's going to be the way that's on this slide that says, so what is conservation of energy? Okay, the way I'm going to phrase it is, conservation of energy is that the energy of a system might change forms, but the total mechanical energy must always stay constant. And now mechanical energy is simply equal to the two types of energy that we've dealt with so far, potential energy and kinetic energy, okay? So I'll call mechanical energy ME. Honestly, from this point on, I'm just going to call it E, right? These are the two main types of energies in the systems, at least, that we're going to focus on, right? But from here on, you're going to see me just call it E. But by E, I mean the total mechanical energy of a system, which means it's sum of potential and kinetic energy, okay? And so conservation of energy just says that for a closed system, right, a system where, other forms of energy aren't being dumped into it, right, this has to be constant, okay? Energy is not simply going to just be spontaneously created or destroyed, right? They just maybe shift form. So you might start out with a lot of potential energy, and that shifts into kinetic energy, or a lot of kinetic energy that shifts into potential energy, depending upon the situation, okay? Now, this little simple thing ends up being so powerful, okay? So here's how we use it. If you guys could go to the next slide. It is, the next slide says the energy skate park. You guys know all about that, but if you want to play more around with it, feel free. So I'm going to give you a 4-step process for solving any conservation of energy problem, okay? You guys know that I love my little, whatever step processes to solve any kind of a problem, and this is another example of that if you follow this perfectly, every time you will get the right answer. You can't get the wrong answer because it's just simply bookkeeping step to step, right? And again, we use that analogy of, energy being like money, right? And so just like you would balance out your checking account, right, you're balancing out your energy account, okay? And so in order to tackle this problem, I'm going to go ahead to the classic old problem that we've been kind of revisiting this entire semester, which is dropping a gumball from the highest building in the world, the Burj Khalifa, okay? And so the reason why I'm using this again, and I apologize if I'm overusing this example, is because you're going to see that by solving this problem, right, so the problem is going to be, what is the speed just before it hits the ground, right? Using conservation of energy, we're going to be able to solve this problem through a different lens, okay? And you're going to prove to yourself by going back in your notes that it's the same exact answer we did when we did this with kinematics, okay? Just shows you how powerful it is. But it's even more powerful because not only am I going to be able to find the velocity here, but I will be able to find the velocity at the 56th floor, and I'll be able to find the velocity if we include drag force, as long as we know how strong that drag force is, okay? So watch me now. Step 1 of every conservation of energy problem, and please, 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 just take my advice on this. It's going to make your life so much easier if you start every conservation of energy problem with just this. E1 equals E2, okay? So what is that 1 and 2? 1 means where you start from, 2 means where you end, okay? So the energy at your initial position / situation has got to be equal to the energy at the final situation. Now the energies may be changed forms, but the total energy, the total mechanical energy here and here have to be the same. So this is the perfect way to start any conservation of energy problem, because it reminds you that all the energies I have here must equal all the energies I have down here, okay? So that's step 1. Always start with that reminder. My total energy that I start with must be equal to the total energy that I end with, right? And this is true at every single point along this path. If instead of here I call 2, I could call it, wherever it's if the gumball's here, I can call that position 2. If it's here, I can call that position 2. At any given point, these energies are always going to be the same. Okay, so that's step 1. If you go to the next slide, we have step 2. You decide what kind of energies are present at your E1 and at your E2. Okay, so right here, if I'm dropping this from rest, okay, if I'm dropping this little gumball from rest, what kind of energies do I have here? Well, I can't have kinetic energy, right? Because it's not moving. There's no velocity, right? Kinetic energy is not there. But I do have a height, right? So that means I must have potential energy. So I'm going to put PE1 right there. Okay, that's the only energy I have here in this initial situation. All right. Now down here, just before I hit the ground, do I have any potential energy? No, I've lost all my height, right? There's no potential energy down there, but the velocity has increased, which means there must be some kinetic energy down there. Okay? And just to point out, anywhere in between, it's some mixture of potential and kinetic energy, right? This guy's dropping at some velocity and he has some height, right? He's got both of those, so there must be some potential and some kinetic energy. But at the beginning, it's only potential, and at the end, it's only kinetic. Okay? That's step 2. We just decide what kind of energies we have here and what kind of energies we have here. Okay? Hopefully that's super, super basic so far. Step 3 is you just substitute the equations of these two guys, right? So we know potential energy is mgh, and it's our initial height, so I put in 1, right? And we know that our kinetic energy is 1/2 mv2 squared, because it's the velocity at the end, right? So step 3, all I've done is substitute my equations. Basic. Couldn't be easier, right? And if there's a situation where you have m in every term, it's just so satisfying to me, like deeply, deeply satisfying to be able to cancel them out. So I can actually make this a little bit easier and say gh1 equals 1/2 v2 squared. Okay? And then I go to step 4, which is just put in your values and solve for whatever you're looking for. In this case, what are we looking for? Again, just like before, we want to find the speed of the gumball before it hits the ground. Well, my friends, g is 9.8. Our initial height is the height of the Burj Khalifa, which I believe we are using 800 meters, right? And that's times 1/2 v2 squared. So I go ahead and I solve for v2, right? Multiply by 2, take the square root of this product, and I get a value of 125 meters per second. Okay? That's my value for V2. And if you go back to the same solution that we did back when we did kinematics, you should see that we still get 125 meters per second. Okay? So 2 different lenses, 2 different ways of looking at the world, and we get the same answer, which I think is pretty cool. Now, here's a question to make it a little bit more complicated. Okay? What if, and if you guys can go to the next slide, it says next level. Find the speed of the gumball as it passes the 56th floor. Each floor of the building is about 3.9 meters. Okay? So next we want to find out what is our velocity here instead. Okay? And we know that this is the 56th floor of this really, really tall building, okay? And we know that each floor is 3.9 meters, so we can find this height here, right? This height should just be 56 floors times 3.9 meters per floor, okay? Now, what do I get when I do that? Well, we'll find out. If you guys want to put that in your calculator now, you may. But this is going to change the problem a little bit, just a little bit, and we're going to see how it changes. Maybe as I erase this, just ask yourself, what is going to change? How is this going to be different? than it was before. Ponder that. Well, here's the thing. Does step 1 change? No, it doesn't. E1 equals E2. Step 1 is always the same. You're just reminding yourself the energy here is equal to, well, instead of the energy being here now, we want to find out the energy here, the total energy here, right? So the total energy here must equal the total energy here. Step 2 is, what kind of energy do I have here, and what kind of energy do I have here? Okay, well, my energy here at the top, that doesn't change either. That's just potential energy. So potential energy 1. He, again, doesn't have any kinetic energy up there because there's no motion, right? There's no speed, okay? So that stays the same. Now, what about here? The gumball reaches this height right over here, okay? Well, in this case, obviously there's some velocity, right? So there must be some kinetic energy there. But unlike at the ground where the h goes away, there's a height here, right? So this gumball, he has potential energy as well. That pretty much is the only way this problem changes, okay? So what do? Well, we do step 3, which is just substitute in our formulas. Again, this is just mgh1 here, okay? This is equal to 1/2 mv squared. That v is 2. We're talking about this v over here, okay? And this new potential energy here that this gumball has is mgh2. Okay? Does that make sense? Again, so satisfying, so enjoyable, just be able to be like, bye, okay? And we've lost our masses. And just a reminder, what does that mean? That means that these problems involving gravity, they don't depend on mass, right? It doesn't matter how much mass you have, gravity is accelerating you at the exact same rate, right? So it could be a gumball, it could be a bowling ball. This is going to have the same velocity here regardless of what you are, okay? So again, we want to find the velocity here. So we're solving for v2. Well, now I'm going to just subtract this over to here. So I have gh1 minus gh2 equals 1/2 v2 squared. My h1 is, again, 800. And I'll go ahead and put 9.8 there. So 9.8 times 800 minus 9.8. And this height, remember, is 56 times 3.9, right? So 56 times 3.9 meters, right? 56 floors at 3.9 meters per floor is equal to 1/2 v2 squared. I solve for my v2 again. I take this, multiply by 2, take the square root, and now I get 102 meters per second. Check it out. Okay. Does it make sense? That should be a question that you get used to asking yourself every time that you actually get a number for an answer. Okay? Does that make sense? And the answer is, well, sure, right? It can't be more than 125 because that's what we got when it fell all the way to the ground, right? It's a little bit less than that. It's 102 meters per second. And so we're like, that seems reasonable, right? Now, if you got something really, really small or something much, much, much bigger than 125, you might want to question yourself. Okay? We're going to be doing many, 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 many more problems involving conservation of energy and how to incorporate non-conservative forces. But this is my introduction to you. I hope you found it as simple, as elegant, and as wonderful as I did.